Yeah, I was just checking.
Just one? Or?
No, there's enough. So I will start. So I will continue where I left off yesterday. Actually, did all of you take one of those sheets to sign and to evaluate these lectures? Or I understand there were some missing. So
You need more?
yeah, anyhow. Ah, okay, they may, okay, probably I left them in the auditorium. Yeah, okay. So yesterday I ended with describing to you the particles states, the many particle states in a Hilbert space, which was called the Fock space. So the next thing I will do is introduce operators that can create and annihilate particles, because that's indeed what happens in real experiments too, is that the number of particles can change. And so we do need operators that can take us from a set of given number of particles to a state which has more particles. So for that purpose we use the creation and annihilation operators. So if I have a state with n particles with momentum k1 up to kn minus 1, and I act on this with a creation operator, which I'll denote with a dagger, and it creates a particle with momentum kn, then we take this state and we obtain the state which has n particles. So we had n minus 1 particles, and then we go to a state with n particles, namely the state where we added 1 particle with momentum kn. Similarly, we have annihilation operators, and annihilation operators are the emission conjugates of these operators. So I'll write them with a, k, n, and if I act with such an operator on a state with n particles, then the state I get will be, and I'll write down this symbol, it will be proportional to the state with 1 particle less. Because the proportionality constant actually is determined by the normalization I gave for the wave functions. And indeed, you can show that this is actually very similar to the creation and annihilation operators that you have in describing a harmonic oscillator in usual quantum mechanics. And indeed, they satisfy commutation relations which are determined, are very similar to the commutation relations of the harmonic oscillator, creation and annihilation operators. So in particular, we find from this that we can describe now any set of any particle state, n particle state, by repeatedly acting with creation operators on the vacuum, we can obtain any n particle state. So this state, for example, can be obtained by taking a string, a set of these creation operators, n of them, and acting all on the vacuum state. So that's a state without particles. Then acting n times with creation operators, we obtain the state with n particles with momentum k1 up to kn. And I described yesterday that the normalization of these states k prime, they were normalized in such a way that there's a delta function in momentum space. So it means that they're orthogonal when they're not equal. And then there's a certain power of 2 pi, first of all, and a function depending on this frequency omega of k. Well, from this we determine actually the commutation relations between the creation and annihilation operators, we get that if we commute A dagger K with A of K prime, well, one way of computing it is actually to take the expectation value of this commutator in the vacuum state, and then using this normalization, indeed you find that this expectation value, well, actually the operator AK, when it acts on the vacuum, because it annihilates a particle, it actually annihilates also the vacuum. So that's one of the equations which I should have mentioned, that the fact that AK annihilates a particle, when it acts on the vacuum, it's equal to 0. And then if I take here this commutator inside the vacuum, you find that the answer will be exactly this normalization of the one particle state. And indeed, that's what the commutation relation gives you, is that the commutator between creation and annihilation operators gives you a delta function in momentum space with the normalizations of the vacuum, of the one particle state. So this is the commutator of A dagger with and A. With a minus sign. Yeah, you're right. The next thing we're going to do is actually look at not just creation of particles with in a certain momentum state, but also we want to create particles in position space. And indeed, one of the reasons why we want to do that is by that we want to describe interactions in field theory. And interactions are, well, interactions between particles should always happen at a certain position in space. So we want to know also where the positions of the particles are. And so in order to do that, we have to go to a different basis of states, which is the coordinate representation. And yesterday I described the wave functions for these relativistic particles in momentum in coordinate space and related it to momentum space. And indeed, that's the way we have to again use that transformation in order to go from momentum space to coordinate space. Well, the objects I want to introduce are indeed operators that create particles and destroy particles at a certain position in space. And the basic objects are the objects indeed that are central in quantum field theory. They are the quantum fields. So let me now come to that important topic. The quantum fields are fields which I'll denote with phi. They are operators actually in this Hilbert space, and I'll denote them by phi x of t. So you can think of them as being those operators that create and annihilate particles at the position x and at the time t. And in particular, when we act with this operator on the vacuum, I want to obtain a one particle state. And the way it's normalized is, again, like the wave functions we wrote down yesterday. It's a one particle state, and one particle states can be written in terms of a sum of the one particle states which I had here. So I can write down it as a sum over states in momentum space, k. But what I have to put in front of it is a plane wave. And I integrate over k space. So I've obtained, by acting with this field on the vacuum, a one particle state, a particular one particle state, which is a sum of momentum eigenstates. But here it's actually the position eigenstate of a one particle. So this is the state that describes a particle at position x and at time t. Yes? So Okay, we have a state, and actually the vacuum state is really a state in the Hilbert space. It's actually normalized in such a way that if I take the inner product of the vacuum state with itself, it's equal to 1. So there's indeed a very important difference between the vacuum state, which is a state in the Hilbert space, and 0, which is not a state. I mean, 0 I can't do anything with. And indeed, if I act on the vacuum state with the creation operator, I get something which you also agree would be non-zero, namely it's a one-particle state. And just like here, if I act on the vacuum state with an operator, I get something that's non-zero. I get a state which has one particle. So the vacuum, you can say, well, it is a quantum state, but it doesn't contain any particle. But what I can do with it is change that state and make it into a state which does contain particles. So the vacuum state is not zero. It's really something that we have to add to our Hilbert space as being one of the states that the system can be in. I mean, we can look at the system without any particles, and we can always create and annihilate particles from the vacuum. Yes? That's a good question. Well, actually, what I've indicated also here is that we always relate the energy to the momentum by the condition that indeed the energy we know how to express in terms of the momentum by the relation E equals the square root of p squared plus m squared. So that's actually what I've indicated here too. Omega of k is always equal to the square root of k squared plus m squared. There's actually a way of writing here a four-momentum integral, but then I have to put in a delta function which imposes this condition. And it's also in that way actually that you can understand why there must be a normalization involving omega k. This is needed in order indeed that this whole expression is covariant and transforms Lorentz invariant. An important thing about these operators is that we want them to be Hermitian. So actually the situation I will be considering first actually will be particles without charge. So no charge and no spin. And in that case, these operators are Hermitian. And that means that if from this I can actually determine already the expression of phi in terms of creation operators, because I know now that creation operators acting on the vacuum give me those states, but I also need annihilation operators. So indeed the expansion that you get, if you write down the field phi in terms of creation and annihilation operators, is the following. It's again an integral but then it has coefficients which are the creation operators plus the complex conjugate or the emission conjugate of this expression, which is containing then the annihilation operators. So it contains both creation as well as annihilation operators. And the creation and annihilation operators do not commute. That's what I wrote down here. There are commutation relations which are non-zero. So also these fields will not commute when you take two of those fields at different points. Then in general they do not commute. But there's a very important condition in quantum field theory, or that follows from relativity, namely that if you take two operators which are outside of each other's light cone, then it's impossible that those operators do not commute. And indeed, so if you look at the fixed time, if I look at two operators which are at different points at a certain time, those two operators must commute. Now from this expression and the fact that we do know the commutators for these operators A, K, it's very easy to calculate actually the commutation relations between two fields at different points. It's a straightforward calculation. And you do find if you take two operators at the same time, and the two operators I will take will be actually this operator phi and an other operator which I call pi, which is simply defined as the time derivative of the field phi. The reason why I call it pi is because the commutation relations between pi of, say, at the position y and t, and phi at the position x of t is very much like the commutation relations between momentum and coordinates, in the sense that there's a delta function. It's just minus I times the delta function of x minus y. And this is often called the canonically conjugate field of phi. So these operators are like, say, the momentum and coordinates in quantum mechanics, but now in field theory. What I described here was the quantization, or this quantum field for a particle without charge and without spin. Actually, if you do have a particle with charge, then what actually happens is that this condition, this reality condition, that the field is Hermitian conjugate, should be dropped. And then the expansion which you get here gives you operators A dagger, but then the operators which you have here need no longer be the Hermitian conjugates of the fields that we have here. And so in that case, what you have is indeed that the field describes more particles than just a single particle. Here, this field would, for example, describe a spinless, chargeless field like the pion, particle like the pion, the pi zero particle. However, if we have charged fields, for example, the pi plus and pi minus pions, then we need a complex field. And for a complex field, the expansion, well, I'm not going to write down the full expression, but what you get is that you get a similar expression as here, where you get an integral over k space, and then you get A dagger times the plane wave, plus, and then instead of having the Hermitian conjugate, namely just A, you'll get some other operator, which is some creation operator, or annihilation operator B, times the other plane wave. So this complex field, which is not equal to its complex conjugate, gives you two sets of annihilation operators, A dagger k and AK, and B dagger k and BK. And these would be the creation operators, say, of the pi plus particle, creation and annihilation part of the pi plus, and you get creation and annihilation operators for pi minus. Similarly, I can add spin, and this I'll do a little bit in more detail, because eventually I want to describe quantum electrodynamics, which does describe particles with spin and charge, namely the electron and the positron. So I'm going to combine those ingredients again and write down for you a quantum field for the electron. So for the electron, which has as its antiparticle the positron, for that we need a spinor-valued field. We already wrote down a Dirac spinor in the previous lecture, which is a 4-component spinor. And so indeed what I will do is write down a spinor field, psi of x and t, which has 4 components and is again expanded in plane waves with creation and annihilation operators. But now we get creation operators which create particles with a certain momentum, but also with a certain spin. So I have to indicate which particle I create, whether it's spin up or spin down. And so I'll give it an index A, which can be up or down. And then there are two kinds of four-component spinors, U of k. Actually, I wrote down for you yesterday the expression for these spinors. So I have two kinds of spinors, namely whether I take chi up to be 1, 0, or with the down to be 0, 1. So these are two-component spinors which can have two basis elements. And so I also have two kinds of spinors here, which I can label and give an index A. And this is precisely the index which I use over there. And then there's a plane wave, the same one which I always wrote down. And then we have more, so I'll continue down here. We have also plane waves like here with the other frequency. So these are the positive frequency modes, and these are the negative frequency modes. And here we have a similar contribution, which is a set of, so these are actually creation operators, which are called C Decker. And then I have a set of annihilation operators, D, which are called D, with a set of other spinor components, VK. Sorry, it's positive frequency, so I'll take the complex conjugate wave here. And so from this expansion of this Dirac field, I get two sets of operators, namely the sets of operators which are called C. And actually expanding its complex conjugate field will give me the other Hermitian conjugate operators of these. So I get the creation operators CKA and also the annihilation operators. And similarly, I get the creation and annihilation operators D. So these are creation operators the electrons, and these particles, they do the same with positrons. So I do get four sets of operators for creating and destroying electrons and creating and destroying positrons. These V's actually are a similar expression as I have here, except where I interchange the upper and the lower components. So you can think of actually as the upper two components as describing the electron states and the lower two components as describing the positron states. So in total, I indeed have a spinor with four components which describe the up and down components of the electron and the up and down components of the positron. Well, this expression actually is a solution to the Dirac equation. So the field psi, the Dirac spinor, satisfies the Dirac equation, which is, I wrote down in relativistic notation. Just to make sure the signs are right. There's an I here, minus m. Psi equals 0. So this is a solution to the Dirac equation, except there's an important difference between these fields and the wave functions which I wrote down before, namely the fields have positive and negative frequencies, while the wave functions that I wrote down yesterday only contain positive frequency modes. So one should not confuse the notion of a quantum field with something that's a wave function. The quantum field is an operator that acts in the Hilbert space and creates and annihilates particles, while the wave functions just tell you something about a single particle where its location is, while quantum fields is something that we can use in the Hilbert space with many particles. So it has a very different interpretation than the quantum fields. But it happens to be that the quantum field satisfies the same equation as the wave equation we had for the single particle fields. So why do we need these quantum fields? The reason we need them is actually to write down interactions. And interactions, as I told you, happen at a certain position in space. And the way we're going to describe it is actually by looking at the evolution, the quantum mechanical evolution of states which contain particles. And if we have a state with a number of particles, then by just the quantum mechanical evolution, we can go to a state with a different number of particles. And the way to do it is to writing down a Hamiltonian that describes to you how to go from one particular state to another state through the Schrödinger equation. So instead of writing down now the Schrödinger equation for a single particle, we're going to write down a Schrödinger equation for states that contain many particles. And in this way, we can look at how a state with a number of particles evolves in time and gives you states, interactions among those particles. So I'll erase this. So for simplicity, I will go back to the case without spin and without charge. So I have a quantum field phi of x and t. And so the Hilbert space of those particles can be some initial state which we want to then look at and evolve in time. And the way to do it is writing down a Schrödinger equation So if we have some state, and what I'll do is actually look at, say, a certain number of particles that come in, but I'll write down the state in a quite general way as just psi of t. So this can be an n-particle state with certain momentum, but it can be some other state as well. And we just think of this as being something like a wave function, but now a wave function for many particles. So I'll write down the Schrödinger equation in the usual way, that if I differentiate with respect to time, then this must be equal to the Hamiltonian h acting on this state. Well, what's the form of the Hamiltonian? Well, part of the Hamiltonian should just describe the way that single particles evolve in time. And so what we have in here will be also the free Hamiltonian, just the way that free particles propagate, because as you know, the Hamiltonian gives you as its eigenvalues the energy, and the energy of single particles is also contained in here. So the Hamiltonian will consist of two contributions, a part which I'll call the free Hamiltonian, then a part which describes interactions. And well, what we want actually is that those interactions happen somewhere local in space. And I'm not going to give you the full derivation of it, but the way to write down Hamiltonians which gives you interactions only local in space is by writing down an expression for this Hamiltonian, which is an integral over space of an expression which contains precisely those quantum fields phi. Actually, the quantum fields that enter in the Hamiltonian can be phi, but also derivatives of phi, in particular also the time derivative which are called pi of x and t, which was dt of phi. And also spatial derivatives. So the expression for this Hamiltonian will be that it's an integral over space over some density, and I'll actually write down this density as curly h, and it's some expression which involves the fields pi of x of x and t. It involves the field phi of x and t, and possibly also derivatives. So it's some expression in these fields which is local in the sense that these fields are all at the same point in space. So they are all at point x, and then we integrate over three-dimensional space. The free Hamiltonian is actually also an expression of this sort, except that it's somewhat simpler. You can write it down explicitly as in terms of the momentum, this momentum field pi and the gradient of phi squared. And then integrate it over space. And this free Hamiltonian is quadratic in those fields, and that's actually why it's a free Hamiltonian, in the sense that if you have an expression which is quadratic in the fields like this, the number of particles will not change, because what it will just describe is the way that particles move through space if there would be no interactions. Interactions occur in this expression if we write down terms which are not, like here, quadratic in the fields pi and phi, but which are higher, involve more powers of the field phi. So they're no longer quadratic, but higher order. And an example of an interaction would be to write down an interaction Hamiltonian, which is the integral, say, of some power of the field phi. Say the fourth power of the field phi would be a typical interaction term that can enter in field theory. So this actually describes an interaction between two particles coming in and two particles coming out, because the number of powers of field phi tells you how many particles should be at the same point to get this interaction. So I won't go describe you many examples yet. I mean, later lectures we'll go into more details of how to write down interaction Hamiltonians that give you interactions. But what I'll take from this now is that we do have an Hamiltonian which we know how to express in terms of the fields pi, phi, and so on, as an integral over some expression, a local function of x. And this Hamiltonian, what we want to do actually is plug it into the Schrödinger equation and then try and solve this Schrödinger equation and see what would be a way to get from an initial state to a final state. Because this Hamiltonian gives you the evolution for all times t, but in an experiment what we see some particles coming in, and eventually we are only interested in the situation of the particles that are coming out. We are not going to measure in any experiment something that's happening in between. So the way that we're going to look at this is by looking at an in state, and we're going to actually idealize this a little bit. We're going to look at the state which is far away in the past, so we have some interaction happening in a certain region of space, and then before that we had some particles coming in, and finally we have some other particles coming out. So we have an in state which you can call psi in, which actually is the wave function of this state psi, say, evaluated a long time in the past, and we'll actually take this to be t equals minus infinity. So we're just going to take some states long in the past, and then we're going to evolve it, and then these particles which are in the initial state, they can interact. Eventually we get particles in the final state, and so we have an out state or a final state, which is the wave function psi evaluated at t equals plus infinity. So what, yes? It does not involve interaction. Should that be obvious? Well, the way to, if I would write this down in terms of creation and annihilation operators, writing down the expressions which I had over here, this would be an expression which is simply written as the sum or the integral. Well, let me write it down in some more detail. I'll erase this. Shift the board, then there's another board here. Well, probably not. Writing down the expansions which I had in creation and annihilation operators, then you find actually that the integral will tell you that it must be an expression where the total momentum, first of all, is equal to 0, and then you get a quadratic expression also in the creation and annihilation operators, because, well, each of the fields were linear in the creation and annihilation operators. So the free Hamiltonian is actually an integral over k of let me write it, yes. Yeah, omega k, and then there's creation an operator and an annihilation operator. So what the free Hamiltonian does, actually, it just annihilates a particle and then creates a particle, but it doesn't add new particles to it. So that's the way to see that this actually gives you the no interactions. And actually, if it acts, the free Hamiltonian, on an n-particle state, it just gives you the sum of the energies of those n-particle states. That's all that the free Hamiltonian does. Yes?
Can you say that it's just what you have in brackets? It's just square of fundamental.
There's a relation there. In a way, it's no, not really. Actually, what it does, it sums up the energies of all of the particles. So this is an operator that doesn't just measure the energy of a single particle, but it measures the energy of a sum of particles. So that's actually the way you should think about. Well, okay, that's a good remark, actually. What I write down here, it is the Hamiltonian, and it may not look relativistically invariant, because usually you have, in relativistic theory, you have the, say, t squared minus x squared or something like that. So the way that goes actually is that the Hamiltonian indeed is not Lorentz invariant, but it's related to what's called the Lagrangian in the following way. If I have a Hamiltonian which is a function of pi and phi, then I can write down a Lagrangian which is pi phi dot, or it's related to the Lagrangian in its following way. it's pi phi dot times as a function of phi, minus the Lagrangian density, which is a function of phi and phi dot, where we define pi as being the derivative of this Lagrangian density with respect to phi dot. Now, if you would write down the Lagrangian density, that would be a similar expression here, but indeed with, first of all, pi replaced by phi dot, and then here there would be a minus sign. I will not go into the Lagrangian formalism right now, but indeed an important advantage of the Lagrangian formalism is actually that so instead of using the Hamiltonian, you use the Lagrangian, but then all the symmetries are manifest and also Lorentz invariance will be manifest. But the reason why I first stick to this Hamiltonian formalism is that because I want to use this Schrödinger equation to write down for you the way we go from an initial state at a certain time to a final state by just evolving the Schrödinger equation, which I have over here. I erased this actually. I hope you got this. So what I want to do is to evaluate, look at the Schrödinger equation, and I'll first write down the Schrödinger equation in what's called the Schrödinger representation. So I'll indicate an S here below my wave function as being the Schrödinger equation which I had over there. So it's the sum of the free and the interaction Hamiltonian which act together on this Schrödinger state. Now the free Hamiltonian is very easy to evolve because, as I already told you, it doesn't change the number of particles. If we would just have this free Hamiltonian, there would not be much to calculate. The interesting thing is, of course, what happens with the interactions. And there's a way of actually separating out the free Hamiltonian and the interaction Hamiltonian by, instead of writing down a wave function, which I call the Schrödinger wave function, we go to another type of wave function in the interaction picture, which I'll call psi t with sub I, which is related to this by just looking at the evolution of the state using the free Hamiltonian H free acting on the Schrödinger state. So this, of course, is not the solution to this equation because this will solve this equation without the interactions. But it's a reformulation, so I'll go to a different set of states which I obtained by acting with this evolution operator on the Schrödinger state. Now, if I take this state and write down the Schrödinger equation in terms of this state, it will actually look differently. In terms of this state, the Schrödinger equation becomes, in the interaction picture, what's it called? It looks like this. So the free Hamiltonian is no longer needed because already taken into account the evolution of the free Hamiltonian, you find only something that involves the interaction Hamiltonian. And I'll abbreviate it actually as H sub I of t So I have a Schrödinger equation which only involves the interaction Hamiltonian. Actually, this interaction Hamiltonian is not exactly equal to the interaction I had over there. is actually the evolution of that interaction Hamiltonian, which you can think of as being just the same interaction Hamiltonian, but now evaluated and at a certain time t. So we evolve it, so it will be a function of t, and that's very important. And the way it is a function of t is actually just like in here, that we have to evaluate this at a certain time t. And I fixed this time t, so we're going to integrate this expression at a certain time t. So this interaction Hamiltonian, that's very important, is a function of the time t. So the next thing to do is to solve this Schrödinger equation. Well, actually, we're not going to really solve it. We're going to do it in a formal way, in the sense that if I know that I have a time derivative gives me the Hamiltonian on this state, just like I did here. If I know that the time derivative gives you the free Hamiltonian, then what I can do is exponentiate the free Hamiltonian and gives me the evolution operator. So in a way, you can solve such an equation by exponentiating the Hamiltonian that's on the right. So I'm going to write down for you the solution. If I have the state psi at a certain initial time, which I call t sub I, which is the initial time where we start solving the Schrödinger equation, and I want to know the state at a certain final time, tf sub I, then the solution is we write down the exponent of minus I times the integral over t of the interaction Hamiltonian evaluated at t. And we integrate from ti to tf. But there's an important subtlety in here, namely that in writing down this exponent, I have to take care that the operators always act in the order in which the time is evaluated. So operators which are at an earlier time should act first on the state, and operators which have a later time should act later. And I'll indicate this with a symbol which is called T, time ordering. And I can write this down actually explicitly as follows, and this is going to be a long expression, which I hope, well, you never really need. What I mean by this time-ordered exponent is the following. It's a sum. We know how to expand exponentials, so I'm going to write down a sum of the exponential in the usual Laurent expansion. And so I'll get a minus I to the power n. Usually I have a 1 over n factorial. I'll actually use that in another way by restricting the integrations which I have. So I have the nth power of this, what's in the exponential, and the nth power gives me n integrations over time. So I'm going to write down n time integrations up to Tn. And I'll restrict these integrations such a way that T initial is smaller than T1, smaller than T2, smaller than Tn, and that's eventually smaller than T final. So I had an initial time and a final time, and all of these integrations are in between those, but in such a way that T1 is the earliest time, T2 is the next one, and Tn is the last one. And then the way that the operators should act is that the operator, which is the last one, should act also the last one as the last operator. So eventually we have n times the interaction Hamiltonian evaluated at different times, t1 up to tn, but precisely in this order, that t1 is acting first, then we have hi t2 up to hi tn. So if I act with this operator on the initial state, I will get the final state. So this is just, well, let's say mathematics, in the sense that what I've just done is formally solved this equation, and indeed what you can do is plug this expression back into this equation and recover the equation which I have over here. Well, I'm going to rewrite it still a little bit further, and the way to do it actually is, first of all, notice that I have here this initial time and the final time. I want to take those times to infinity, into at least to ti, the initial time to minus infinity, and the final time to plus infinity. And furthermore, I have an expression for the interaction Hamiltonian, namely the interaction Hamiltonian is an integral over space of some Hamiltonian density. So I'm going to plug that in as well. And then you see I have here an integration over space, and here an integration over time. So eventually I'm going to integrate over space and time. So this equation here becomes the following equation, that if I have psi at minus infinity must be related to, plus infinity, must be related to psi at minus infinity with an expression which is the time-ordered exponent of minus I, and then I have an integral over space and time, so indicated with d4x, and then I have the interaction density, Hamiltonian density, which is an expression like this, evaluated also at a certain point in time and space. So now I've used x as a notation for both space and time. And the object which I have here is called the S matrix. Because it describes the relation between the initial states and the final states, and describes the interaction part of it, because it only depends on the interaction Hamiltonian and not on the free Hamiltonian. And indeed, the way that we can evaluate it will, will be part of what, of course, field theory is about, and is the way that we evaluate corrections in field theory, namely through Feynman diagrams. That I'll actually leave for the next lecture. The objects we want to evaluate are, of course, always, say, related to a certain concrete situation where we have, say, initial states and final states with certain momentum, particles, say, with certain momentum. And so the amplitudes that's going to give me the probability of going from a certain initial state to a certain final state is something that involves this operator. So let me write down the S matrix really as a matrix, because maybe you're wondering why we're calling it a matrix in here. And I'll write that down here. So if I have a certain initial state, psi initial, say, which is an n particle state with momentum p1 up to pn, and I have a final state which has a different set of number of particles with momentum, say, kn up to kn, km. So this is a process where we have m particles going out and n particles going in. Then the amplitude between these two initial and final states, now my notation is, well, there's an amplitude describing the transition from this initial state to the final state. And actually, it's written in terms of these Fock space states, which were just the free Fock space states which have n particles and m particles, which I introduced in the beginning. Actually, that can be evaluated by, this amplitude can be evaluated by taking these states and writing down precisely that operator which I have over here in between those two states. So I have the final state and the initial state, P1 up to Pn. And then I have the time-ordered exponential of minus I, the integral over 4 space of this interaction Hamiltonian. So I take this interaction Hamiltonian, which was an expression in terms of all of those fields. In particular, there were not quadratic expressions, but could be higher order in the fields, and I can expand those fields in terms of the curation and annihilation operators. And then I let those operators act on the state on the right, and I just evaluate what's the probability of getting the state on the left, which is then the final state. And this amplitude is something that I can use then eventually to compute the probabilities for having certain outcome in experiments. For example, then the cross sections are determined in terms of these amplitudes. So next time I'll start from here and tell you more about the way that we do evaluate those amplitudes using Feynman diagrams. Are there any questions at this moment? And I'll Okay.